In this next section, I'm going to continue with that same workplace, but now we'll focus on process operator number 2. And here, again, the process operator number 2 is responsible for some other tasks, and we have now collected some full shift air samples for xylene, just the same as for the first example, and we'll now do some Bayesian decision analysis. We now have, again, as before, 3 data points, and 1, 65, and 0.5. And we'll again start with a non-informative prior, and the likelihood function shows that there is 71.6% probability in category 2 and 3.5% in category 4. So we could say, okay, that looks pretty decent. It meets our criterion for acceptability in category 4 and it's clearly a category 2 exposure. Now take a look at the data, and we have 3 data points, 1, 65, and 0.5. And clearly one of them is much, much greater than the other 2. So does that cause any discomfort to us? We could interpret this very straightforwardly, as I said earlier, that we have less than a 3.5% probability that process operator 2 requires additional respiratory protection. And looks like it's acceptable, but like I said, let's take a closer look at the data. We could look at the traditional statistics page of the software, and we see on the right-hand side at the top, the geometric standard deviation, GSD, is in fact 13.9. So it's clearly very high, and in fact beyond our parameter space. If you recall, our parameter space has the GSD bounded at 4, and we are clearly well beyond that parameter space. So what is the impact of this on our analysis? So on the right-hand side, I'm showing you the parameter space for the likelihood function corresponding to these 3 data points. And you can see the peak of this rising, and it looks like the peak is going to be well beyond our GSD of 4. And so the peak of this distribution for the likelihood function is well beyond our parameter space. And clearly that's not really desirable. So our GSD is exceeding our GSD max. So what I'm showing in this slide are 2 sets of parameter space and the likelihood function. So on the left-hand side, we have what I've already shown you. The peak of the distribution is beyond our GSD max of 4. But let's say that, okay, that's not a good place to be at. So I'm going to increase the GSD max for my parameter space by going into the software tool. And now I increased it to 16. And now I'm again looking at the 3-dimensional likelihood distribution function. So now we can see that the peak is well within our parameter space because we increased the maximum to 16 for GSD. But now if we look at the probabilities in the different exposure categories, we see that this is clearly an exposure category of 4. There is almost 50% probability in category 4. So what this is telling us is that the default parameter space may not always be the correct one. And we always need to check the traditional statistics page and make sure that the sample GSD is well within our parameter space. So why is this a category 4 exposure and not a category 2 exposure? Well, if you go back to our 3 data points, which is 1, 65, and 0.5, we see that this is a highly variable data set. Some data points are very low, and at least one data point is very, very high. And given this high variability in our data, we can clearly expect that the 95th percentile is going to be well beyond the OEL of 100. So it matches our common sense that in a very variable data set, we are likely to exceed the OEL. And so this makes it very likely that we are looking at a category 4 exposure. So again, like I said, in this example, we had to go in to the software, to the parameter space for the universe, and in the universe boundaries tab, we looked at the GST max on the bottom of the right-hand side of this slide and set it to 16. So what might be going on with process operator number 2, and which tasks might be creating these issues? Should we institute a task-based sampling strategy, and which tasks? So you can see these are the questions that the Bayesian decision analysis prompts us to consider. So this is just to emphasize that the BDA tool by itself is not the answer to all our problems, but it is guiding us in troubleshooting and better understanding our scenario. And so it looks like, well, there are maybe two types of tasks that this worker is doing, some that are leading to very low exposures, but occasionally there might be very high exposure tasks. And so that's maybe something that will prompt us to look at a task-based sampling strategy. Like I said, always check the sample GST to make sure it does not extend beyond the universe parameter space. And watch out for what people consider outliers. One of my messages is it's very easy to dismiss the data point 65 in our 3 data points as being an outlier, that's not something that normally happens. But in fact, it happened normally enough that it was 1 out of the 3 data points. And so we should not dismiss values that are high just because it doesn't match our expectations. If you remember, this is a log normal distribution, which means that very high values are also likely to happen, although at lesser frequency or with lower probability. And so when we have GSTs that are greater than 4, then it might be better to consider task-based approaches. So the BDA software also allows you to put in custom built or professional judgment priors. And you can use either one of these two options. So in a professional judgment prior, when the user picks an initial rating and a certainty level, a recommended prior decision chart is shown. And you may or may not agree with it, so you can decide to go with it or not and have your own custom probabilities. But let's say that you decide to go with the defaults that are built into the software. And so if you want a non-informative prior, that's of course a uniform or flat prior, as they're sometimes called. So 20% in each of the 5 categories. But let's say your initial rating is a category 1, but your certainty level is low, meaning you're not that sure that it is in fact a category 1. Then you can see that the second chart from the top, that corresponds to a category 1, certainty level low. And then you have the next chart, category 1, certainty level medium, and then certainty level high at the bottom. And you can see the differences between these are primarily the height of the probability in category 1. So as our certainty level increases, we have more and more probability in category 1. And the lower our certainty level is, the less probability we put in our category. And it is approaching a flatter prior. So as we increase in confidence, we have more probability in a particular category. And this is true in the next 2 slides. So here we are looking at category 2. So when we have certainty level low, we have only 40% in category 2. When we have medium certainty level, we have 50%. And then we have high certainty level, we have 60% in category 2. And notice that we don't go above 60% in our priors in any of these default settings. And that is a good practice to have. We don't want to be overly certain about any category because we should not ever be that certain. As we discussed in a previous lecture, this is the mark of what we call an intelligent prior, meaning we should have a high enough probability in a given category, but not too high that it overcomes the decision by our small number of monitoring data. And this is the set of charts corresponding to category 3 for low, medium, and high certainty levels. And then category 4 for low, medium, and high certainty levels. But if you don't like any of those probabilities, you can have your own custom prior. So on this slide, I'm showing screenshots for when you can input your own custom probabilities in each of the 5 categories. So on the right-hand side, we see the probabilities that you can enter in each of the categories 0, 1, 2, 3, and 4. They still need to add up to 1, but that's the only condition. And they are your own probabilities rather than the defaults that are provided by the software. But like I said, it's important to keep in mind to have quote-unquote intelligent priors. So a professional judgment or a custom prior decision chart can be used to reflect the initial rating and certainty level assigned to an SEG before the data are collected, or from data that may be considered representative.